Today we're kind of wrapping up all the different transformations that we've done. You can see right here that it's already talking about vertical and horizontal transformations. So this page wants you to go through and match up what we've been talking about. They already have an example on a couple, such as here, if k is greater than 0, when we have f of x plus k, then we're going to translate k units, or up by k units. So I want you to try and fill these out first. Remember what is vertical, and we're talking about translation, and then horizontal, how you translate, and then go on to vertical and scaling. Vertical scaling, horizontal scaling. Take a little bit of time, see how much you know. This is just kind of a quiz for yourself. If you understand all of it, then that's great, and you should have a decent understanding of it. If not, then this is something to maybe star and say, yeah, I didn't quite understand it. But this is a good review page to come back to and look at everything that we've been working on. So I'm going to give you a little bit of time, try this, and see how it goes. Okay, so I'm going to start filling out this paper for you. So the first one here is vertical scaling. We have f of x plus k. So when k is greater than 0, we're translating up. But when k is less than 0, we should be translating down k units. So when we look at horizontal, we're going to have y equals f of x plus k. So on this one, we're going to see that now we're doing x plus, or actually it's not even plus k, my bad. It is minus k. It is minus k. Because on this one, we're subtracting k from the inside, and it's going to move our horizontal graph, our graph horizontally. So horizontally, when k is greater than 0, we translate right by k units. When k is less than 0, so we have a negative number. You can even put these on here just to kind of remind you. When k is less than 0, we're going to translate left by absolute value of k units. Okay, the next one we have is vertical scaling. So we have scaling. Vertical scaling is y equals k f of x. So when we look here, when k is greater than 1, we're going to have a vertical stretch. Vertical stretch by a factor of k absolute value of k. Erase that. Okay, so we have a vertical stretch by a factor of k. From 0, or if k is greater than 0 but less than 1, we have vertical shrink by a factor of k. So this one's going to be fairly similar. It's -1 is less than k is less than 0. So if k is between -1 and 0, then we're also going to have a shrink, and it's going to reflect over the x-axis. So for this one right here, k is less than -1, then we have a vertical stretch again by a factor of absolute value of k and a reflection over the x-axis. Okay, now we're going to move on to the horizontal. This is the one we talked about last lesson. So this one is k is greater than 1. We're going to have a horizontal stretch by a factor of k. And then if it's less than 1 but greater than 0, it's a horizontal shrink by a factor of k. So horizontal shrink by a factor of, I'm going to put this on the outside, absolute value of k. So Then it talks about horizontal shrink and reflection over the y-axis, and then a horizontal stretch by a factor of k reflected over the y-axis as well. So this page is going to be perfect to study with when we get to the test and just look back and say, okay, how does this create different translations? So this one, I would star. Another thing that you can use to look and see how these transformations are working, I haven't really told you about this yet. Some of you may have done this already, but it is using Desmos. You can plug in the different equations and then at plus B. If you click B, then there should be a slider underneath and you can change and see how it'll change the graph. That's something I'll show you guys probably when I get back. That way you can see how this works. But Desmos is another way that you can go in there, practice with these, just visually see how subtracting or adding different things in different places can change the graph that you're going to get. So, like I said, this lesson is kind of bringing everything together. So we're moving also back to piecewise functions. So this exploratory challenge 1 kind of gives us a reintroduction into piecewise functions. And so it says a transformation of the absolute value function f of x equals the absolute value of x minus 3. And it is rewritten here as a piecewise functions, describing words how to graph this piecewise function. So we talked about earlier how you can create these graphs and make it into piecewise functions. You just have two separate lines. You have your first line for this one that'll have a negative slope, and then you'll have a second line with a positive slope. As you can see here, negative slope and a positive slope. So if we were going to graph or explain this in words, you could say first the equation f of x equals negative x plus 3 is, I'd say, used for values, and it just says less than 3, so we'll say less than 3. Then the equation f of x equals x minus 3 will be used for, I'll erase that, values equal to or greater than 3. So this one right here, this is just kind of how you would, really how you describe it. If I was to ask you, how would we graph this? You'd say we're going to use the top equation or this equation here if our values are less than 3. If they're greater than 3, then we're going to use this bottom equation. So that's just kind of how we would talk about it. So this next part, it talks about you graphing. It just gives you a little bit more experience, a little bit more practice with graphing a piecewise function. So right now, I want you to take the time, try this out on your own, see if you remember how to graph a piecewise function, come back to the video, and I'll graph it out for you. Okay, so when we're looking at this, we're going to start at, well, it has to be values less than negative 2. So we can plug in negative 2 because it'll equal, and we can see what we're going to get. So it doesn't hurt to also have a function table off to the side. So we're going to have negative 3x minus 3. So if we plug in negative 2 times negative 3, I want to write this over here. Negative 2 times negative 3 is going to be 6. Minus 3 is going to end up being 3. So that'll be the point there. Then we can plug in negative 3. So negative 3 times negative 3 is going to end up being 9. 9 minus 3 is 6. So we can kind of start seeing that we're going to be increasing by 3 every time we go back. So if we go negative 4, it's going to be 9. And that should be enough. That will get us on this chart. And actually, if we go any more, it'll go outside of the chart. So this is our first line. So then the next one, so just put a second. Now we have a set limit of which we're going to go to. So from -2 to 2. Remember that we need to figure out where these points would go to. So I'm going to plug in -2, but off to the side I'm going to write or draw an open circle so that I remember that we can't fill that in. I'm also going to put -1, 0, 1, and 2, and again put an open circle to the side. We can't end up filling it in unless these other equations equal that point exactly. So if we plug in -2, it's going to be -1, because you're going to do 1.5 times -2. So -1 plus 4, that's also going to equal 3. So we will end up matching up, but I'd still write this off to the side just to remind yourself. So then the next one, we're going to plug in -1. -1 times 1/2 is going to be -0.5 plus 4, so 3.5. And then we're just going to keep on increasing by 0.5. So 4, 4.5, and 5. So that'll be our next one. And then our third line, we're going to do from 2, and we'll go from there for a little bit. So x, y, probably should label that one. So now we're going from 2, 3, 4, and we'll stop for there. So if we plug in 2 times -2 is going to be 4 plus 9, 5. And then 3, so 3 times -2 is -6 plus 9, that is going to be 3. So you can start to see we're decreasing by 3 every time, or by 2 every time. So the next one would be 1, if we go to 5, -1, 6, -3, and we'll stop there. That'll be good. So I'm going to graph this, the first one, in pencil, the second one in this blue pen, and the last one in a red pen, just so you can see how these will look differently. So for this one, -2, 3, so 1, 2, 3, and this would be a closed dot. So the -3, 6, so 1, 2, 3, 4, 5, 6, and -4, 9, so actually I can just go up 1, 2, 3, back 1. Okay, so we can draw a line between those points as any of the values will work there. We could continue it up, but we won't worry about that one. So then the next one. So -2, it's going to be a 3. So it would be an open circle around that point, just drawing it out to show you. So then -1 would be at 3.5, 0, or whoops, wrong way. 3.5, 4, and we'll just put the other point at 5 right there. I'm having a tough time with this one. Actually, that's not going to be a filled in dot, it'll be an open circle. So I'll just create them to an open circle. So there would be the line between those points. So the last one is going to be at 2, 5. So at 2, 5, we fill in that open circle. And then at 3, 3, so down 2 over 1, down 2 over 1, down 2 over 1, and down 2 over 1. That should get us to 6, -3. So we can draw the line through there. So again, that's just giving us some practice with piecewise functions again. We're going to use piecewise functions and transform them. So we're going to, again, practice this, writing out different formulas from a piecewise function. So again, pause the video, take the time to practice this on your own. This is good practice writing linear equations. I will say that this part right here can be written 2 different ways. You can either say these are separate lines, or you can say it's an absolute value. Either one works, and that's just kind of up to you to figure out how that one would work.